Hello, in this video we will try to find out the derivatives of a trigonometric functions and what we can do, what tools we have. Okay, let's see. One of the tool is tangent line. We know that the slope of the tangent line represents the value of the derivative at the given point. We also have a definition, the limit definition of a derivative, but let's start with a slope of the tangent, okay? And then we will try to also use the definition. That means the first trigonometric ratio, the first trigonometric function, sine of x. Y equals to sine of x. And you may notice I did prepared everything. The blue curve is the curve of sine of x, and the horizontal lines are the slope, are the tangent lines at these particular points. Pi over 2, we know that function attains maximum and local maximum, and then we do have a horizontal tangent. Horizontal tangent means that the slope is 0. Another horizontal tangent, respectively, will be in this point, 3 pi over 2. And then, since the function is periodic, everything repeats. For negative pi over 2, also horizontal tangent, slope 0. And one more, 1, 2, 3. Oh, negative 3 pi over 2, also horizontal tangent. Since the slope is 0, the value of the derivative will be 0. 0, 0, 0. Okay, now I also draw tangent line here, okay, like at the point 0. And we may calculate this, but I will tell you that this slope is 1. And respectively, this slope is also 1. This slope of that tangent is also 1. That means now we can get corresponding values for the derivative. The value is 1. Value here is 1. Value at pi 2 pi, it's also 1. Now, symmetrically, this slope is negative 1. This slope is negative 1. And then the corresponding values for the derivative, negative 1, negative 1. Okay. Now, let's see what's happened between these points. For instance, let's look at maybe here. When the slope is 0 here, the slope of the tangent. Now, drawing a couple of tangents between, we can see that the slope of the tangent increase, and it's getting steeper and steeper and reach 1. That means the values will increase, because that's the corresponding slopes, and reach 1. And then again, it's getting less steeper and it's approaching 0. Values are getting smaller and approaching 0. That means that pattern we can repeat between every other zeros, every other horizontal tangents, or when we're talking about the derivative, every other zeros. That's what we can see now. I can plot, which actually we did have the graph at the beginning. I can connect all of these points, and this is the graph of the derivative of the sine of x. Okay? And if we look at this graph carefully, we may notice, yes, this is derivative, and this is sine of x, and this graph looks like cosine of x. Okay, that means this is the first formula to remember. Derivative of the sine of x is cosine of x. I also typed the proof based on the limit definition. Okay, we know limit definition looks like this. Derivative of the function f is equal to limit as h goes to 0, f of x plus h minus f of x over h. And now when we evaluate for the sine of x, we can see that's one step. Then we need a couple of trigonometric identities. That means you can maybe pause the video or you can look at the notes and you can see what I'm doing. Probably everything is relatively simple. Okay, because I use the sign of the addition of two angles. That's the angle, that's the formula we can see here. Then I split for 2. fractions, and then I'm again splitting for some product, and then we will have a limit of the sine of x, limit of cosine of x, and limit of sine of h over h. As we definitely recognize that limit from I believe chapter 2, the limits of the functions. That means this limit goes to 1. And we also have a nice big limit like this one, which I'm solving on the side, okay? But this limit is basically 0. It's relatively easy to compute this limit, this part, okay, if we use the L'Hopital rule. Yeah, but probably we still don't know the L'Hopital rule, then we can just use the algebraic approach. This is indeterminate form. The limit creates the indeterminate form because cosine at 0 is 1, 1 minus 1 is 0. Theta is 0, 0 over 0. But we know that indeterminate form 0 over 0 can lead to different answers. 0, maybe infinity, maybe negative infinity, maybe a finite number, non-zero finite number. In this situation, we have 0, but we do have a proof. And also it's worth to remember how we can evaluate this limit. We can multiply by the conjugate expression of cosine of x, cosine of theta minus 1, cosine of theta plus 1, and then do the algebraic steps, couple of trigonometric identities, and we're getting 0. Of course, it's very simple to use the L'Hopital rule. I will put h. We know what this means. Theta goes to 0. We just need the derivative. Derivative of cosine theta is negative sine theta. Derivative of 1 is 0. Derivative of theta is 1. And now when we do the direct substitution, sine of 0, and this is 0 because we do not have 0 in the denominator. That's when we may use it, or we can just focus on algebraic operations. Okay, that means yes, that limit is 0, and then limit of the sine of x as h goes to 0, sine of x doesn't include h, then this limit is constant. Limit of the constant is just that constant because we don't have h. Sine of x is constant with respect to this limit. Okay, that means this is sine of x. The same for this one, cosine of x, and that limit is 1. Okay, that's what we got. Derivative of sine of x is cosine of x. Okay, that's it's interesting. You may even not look at this solution. You may try to repeat on your own. It will be fun. But if we understand, let's come back. If we understand the slope of the tangent, it's also good. That means for the cosine of x, that's sine of x. Derivative of sine of x is cosine of x. From now on, we will remember this forever. Okay, cosine of x. Well, my graph is, now we have to do everything from the scratch. But what we will do, we will still use the slopes of the tangent lines. That means this is cosine of x. Let's be a little bit more, let's label pi 3 pi over 2 and 2 pi. And then negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, that means now we know the steps, and this will be derivative. Okay? Okay, that means maybe I can use green color. Okay, at 0, horizontal tangent, then the value of the derivative will be 0. At pi, horizontal tangent, value of the derivative will be 0. 2 pi, horizontal tangent, value of the derivative 0. Negative pi, horizontal tangent, then value of the derivative 0, and 1 more. Beautiful. Okay, now we know that that slope is 1. I can maybe write 1. Then value of the derivative 1. Slope negative 1. Value of the derivative negative 1. And so on. 1. And this will be negative 1. Okay. And what we have? Negative 1. Okay. And now what is happening? Let's just look at one section between zeros. Maybe here, this is 0. Okay, and the slope of the tangent is increasing. Yes, slope of the tangent is increasing, reaching 1, the value 1, and then it's again getting less steeper and reaching 0. That means this is the curve, because when I connect these points, I'm getting that curve, and will be the same, decreasing and increasing, decreasing and increasing. That's the value of the slopes. Okay, beautiful. And this is pi over 2 pi, 3 pi over 2, 2 pi, negative values. Okay, and what we see? Who can help me with the graph? I know that everybody's watching this video, and I mean, who can help me with the formula of this graph? Looks like, yes, looks like sine of x, but flipped. Yeah, because sine of x, I can maybe draw it. Sine of x looks like this. That's sine curve. But the green one, which is the derivative, is flipped. And flipped means that we will put negative sign, yes, for the transformation. Sine of x with the negative sign. Okay, another formula. Oh, derivative of cosine of x is negative sine of x. Cosine of x, yes. Derivative d dx, derivative of cosine of x with respect to x is negative sine of x. Another formula to remember. Okay, now, tangent. Tangent of x, I don't know if will be easy or like, I think it will be a little bit confusing when we will try also to look at the graph and the tangent lines, because we know it will be so steep. Tangent, yes, function, tangent of x. Everybody knows the graph, looks like this, and then it's repeating every pi. And if we think about the tangent, we don't even have 0. It's like really, really steep. Function is increasing, that means everything will be positive, but I don't think we can really get the values like for sine and cosine. That's what we can do. You probably see the instruction. Let's use the quotient rule. We know the quotient rule. We know that tangent of x is sine of x over cosine of x, and we know the derivatives of sine of x and cosine of x. We just learn. That's mean, let's see. Quotient rule. Derivative of the function from the top, yes, times denominator, function from the denominator, minus derivative of the denominator times the function from the top numerator, and denominator squared. That means that step is a quotient rule. Okay, and let's see. Derivative of sine of x, cosine of x. Copy that cosine. Minus derivative of cosine of x, negative sine of x. We just learn. And sine of x. Cosine times cosine is cosine squared. Negative and negative becomes positive. Sine of x times sine of x, sine squared. And what we see on the top? You can answer aloud. I will hear it. I will hear it. You can see that this is just one Pythagorean identity for the trigonometric functions. And we may leave it like this. That's the derivative of tangent of x. However, we have another trigonometric ratio that represents the reciprocal of cosine of x, secant. Secant square of x. This is derivative of tangent. That's the third formula to remember. Okay, tangent of x, derivative of tangent is, did I type? Oh no, I didn't type the, let's write derivative with respect to x of tan of x equals to secant square of x. Beautiful. Okay, the third formula. And now what I have, I did the same way, and I use the quotient rule for cotangent of x, cosecant of x, and secant of x. Okay, but what I will do, I will quickly go through because I want you to do it. Okay, the same way, you know, and we only need derivative of sine of x and cosine of x and the quotient rule. That means you can even practice this again. Okay, cover the solution, practice, and now cotangent. Okay, that means now you have to show me that step. The quotient rule for cotangent, quotient rule for cosine of x over sine of x. Derivative of cosine times sine minus derivative of sine times cosine, and denominator squared, which is sine of x squared. Okay, that means please pause the video or look at the notes. Please pause the video at the moment, yes, for this, at this moment, get the derivative, and then we can compare. Okay, I hope you are back. I hope you did pause the video. You are back, and what you have? You have this, 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 and this. Beautiful. Okay, you can even repeat one more time. It's an excellent practice. Practicing trigonometric formulas and quotient rule. Cotangent of x, derivative of cotangent, derivative with respect to x of cotangent of x is negative cosecant square of x. Yes, the negative is not squared, because if the negative will be squared, we will not have that negative, that's squared. Okay? Now, secant. Secant of x is 1 over cosine. Again, you pausing the video at the moment, okay, and you're trying to use the quotient rule. On the top, on the numerator, we have function 1. 1 is a constant. Derivative of the constant 1 is 0. Okay, that's in pause the video. Okay, and I hope now you come back. Okay, you did come back, and you have this derivative of 1 and cosine. I mean, all of the steps. You have this, and now you got this sine of x over cosine of x times cosine of x, which we can say, yes, it's sine. We can say this 1 over cosine is secant, and sine over cosine is tangent, because this will be the easiest way to remember derivative with respect to x of secant of x. Derivative of secant of x is secant of x times tangent. Excellent. And we have one more, the last one, cosecant. Cosecant of x is 1 over sine of x. You can pause the video. Please, 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 please pause the video, and now you are back, okay? And you have all of these steps, just the quotient rule. This one, this one, this one, this one, and the same analogy. Negative 1 times cosine, negative cosecant of x times cotangent. So the last formula for today is for this video, because maybe you will practice different formulas also. Derivative with respect to x of cosecant of x is negative cosecant of x times cotangent. Excellent, excellent. And that's all of them. That's what we have to know from this, yes, from this section. The definition, I mean formulas of the derivatives for the trigonometric function. And you may notice all of the cofunction, cosine, cosecant, and cotangent, they have negative sign in the formula for the derivative, for their derivatives. Okay, cosine negative, cosecant negative, cotangent negative. Just a pattern. Okay, that means now we know all of this. We have to remember them from now on, forever. Okay, and now let's just do maybe a couple of exercises. I have those, okay, exercise number 1. I mean exercise number 1, 2, and 3. Okay, differentiate x squared sine of x. Okay? That's the important part is not to miss the product rule. Okay? I just said, but we have to be extremely careful. That means what we need derivative of x squared is 2x times sine of x plus x squared, and derivative of sine of x is cosine of x. And I think I typed this. Beautiful. Product rule, because we know the dot is not really printed. But we have to product. Please, yeah, that's the one of the most missed question. Okay, exercise number 2, cosine of x over x. This one, I hope we will not miss the quotient rule. We have so much practice with the quotient rule. Okay, derivative of cosine of x, negative sine of x times x minus cosine of x, derivative of x, 1, and denominator squared. Beautiful, and we can rewrite like this. Always when we multiplying function sine, like trigonometric functions with like additional expression, additional function, please place this in front. Yes, because we know sine of x is not an algebraic function, we cannot really combine this. That x is sitting, yes, that x is totally different. I mean, it's the same independent variable, but has a different role than this one. It's the same value, of course. Okay, and now, exercise number 3, tangent of x plus cosine of x over sine of x. That's what we can do. We can still apply the quotient rule right away, but also when we see trigonometric expressions, we can always think if we may rewrite, simplify. Right? That's what we will try to do before the derivative. Tangent of x is sine of x over cosine of x. Let me write. And this is sine of x. Equal sign supposed to be at the level of the main fraction bar. Okay, and now we can divide. We can write sine of x, cosine of x over sine of x, and cosine of x over sine of x. I will actually remove this. Okay, that's we can see, how can I write? Sine of x over cosine of x and over denominator, and then cosine of x over sine of x, because I wanted to cancel this one. That's what we have. We did, I think we will avoid the quotient rule. This one will stay 1 over cosine, which is secant of x, and cosine over sine is, oh, I typed here, okay, it's okay. Actually, you have on the video. We can do this way, then it will be a little bit, I mean, you have in the notes, and I mean in the video also. Tangent of x over sine of x can simplify to secant, and cosine over sine, it's simplified or rewrite in terms of the cotangent of x. And now we just need the derivative. Derivative of secant of x, secant tangent. Derivative of cotangent, cofunction, negative cosecant square of x. Beautiful. Yeah, that's good. Okay, what else I have? I think I have 10 exercises, but let's see if we can solve all of them. Okay, exercise number 4. You can always make a pause and come back later, or you can just finish the whole section about trigonometry, derivatives of the trigonometrics. Okay, what we have here. For what values of x does the graph of f have a horizontal tangent? That's mean where are the horizontal tangent? If we will get this question, always the general settings is horizontal tangent is happening when the derivative is 0. Yes, we remember horizontal tangent, derivative 0. And now this is the function secant of x over 1 plus tangent of x. Okay, that's it. Let's see, we have to find derivative and we have to set up derivative to be equal 0. Okay, that means this is the derivative, quotient rule. We cannot simplify this one. We may rewrite in terms of sine and cosine, but let's just leave it like this. Derivative of secant, secant tangent, times denominator, minus secant times derivative of the denominator is secant square of x, and the denominator squared. Me saying denominator, I mean, I have in mind function from the denominator. Okay, now what we see, this is subtraction. Secant of x and secant of x is a common factor. Let's factor out. Because we definitely need to have a product form, factored form. Okay, now we have tangent times 1 plus tangent minus secant square. Let's distribute tangent of x times 1, tangent of x times tangent squared minus secant. Now we can rewrite possibly secant squared. We know from the Pythagorean identity that secant squared is equal to tangent square of x plus 1. That's mean let's rewrite. Since we have negative, we will put -1, negative tangent square. This is cancel out. Okay, that's mean now we got secant of x and tangent of x minus 1 on the top. Now, derivative is 0 if the numerator is 0, because we're just looking where the derivative is 0. That means this is numerator, secant times tangent x minus 1, and that product is 0 if tangent of x is 0, I mean secant of x is 0, or tangent of x minus 1 equals to 0, meaning that tangent of x equals to 1. Okay, secant of x, when secant of x is 0, we know that secant of x is never 0. Yes, if we think about the graph, or we can also think 1 over cosine, this will be never 0, no solution. But when tangent of x is 1, of course, for 45, pi over 4. And this will repeat every pi. Pi over 4 plus 1 pi, pi over 4 plus 2 pi, and so on. Okay? That means at pi over 4 and every other, every pi, we will add pi. The graph of this function has a horizon. Okay, now let's do exercise number 5. Okay, we have to find the derivative of secant of x times tangent of x. And actually, I can leave it for you, but please remember, apply the product rule. Because again, it's easy to miss. And let's do the product rule, and we know derivative of secant, we know derivative of tangent. Okay, that's your turn, and you can check the solution later. Okay, now exercise number 6. Find the slope of the tangent line to the given curve at the point P. For exercise number 6, the point P is pi over 2 pi, and the function is 2x sine of x. That means basically slope is the derivative at the point x, at the point pi over 2. Okay, that means let's try to do this one. Derivative of the function 2x sine of x. 2 sine of x plus 2x cosine of x. You probably notice I did apply product rule. And now let's just check our unit circle information, knowledge. X is pi over 2. Pi over 2 and cosine at pi over 2. Okay, sine at pi over 2 is 1. This one can be cancelled out. And cosine at pi over 2 is 0. Okay. Slope is 2. Beautiful. Really nice exam type question. Okay, and then exercise number 7, the same thing. We just have to find the derivative of secant of x at pi over 3. Exercise number 8, we have to find a second derivative for secant of x at pi over 4. Okay, that means you can also do this. And oh wow, well, exercise number 9, we know that function f at pi over 3 equals to 4. Derivative of the function f prime at pi over 3 is -2. And now we have these two functions, g and h. Function g of x is defined f of x times sine of x. Function h is cosine of x over f of x. And we have to find out the derivative of g and derivative of h at pi over 3. That's it. Let's maybe I will do one of them. And you will do another one. This one requires product rule. This one needs the quotient. That's it. Let's maybe do the quotient. You will do the product. I will do the quotient rule. Okay? Okay. Derivative of h of x first. Quotient rule. Derivative of cosine, negative sine of x times f of x minus cosine of x times derivative of the denominator, and then function from the denominator squared. Beautiful, that's it. Now we have to just substitute negative sine at pi over 3. times the value of the function at pi over 3. Cosine at pi over 3, value of the derivative of f at pi over 3. And then value of the function pi over 3 squared. Okay, the same you will do on the left-hand side for product. Okay, now sine of 60 degrees. Sine of pi over 3 is square root of 3 over 2. F at pi over 3 is 4. Minus cosine at pi over 3, cosine at 60 is 1/2. Derivative of the function f at pi over 3 is negative 2. Okay, and now value of the function is 4 squared. And let's get the final answer. This one will be negative 2 root 3. Negative and negative is positive, and that's actually 1/16. I think we can leave it like this, or we can say 1 minus. When we have one quantity positive, one negative, we can always place the negative as a second one. Okay, really nice. And then you can check later the product. Please do it. Okay, and then we have the last exercise. Oh no, we have actually 11 exercises, but okay. What about this one? I'm sorry, I think I said 10. We have 11 because the 11th one is really important, as always. The last one is really important. Okay, find the 27th derivative of cosine of x. Oh, well, okay, let's see. Function is cosine of x. First derivative is negative sine of x. Second derivative is negative, and derivative of sine is cosine of x. Third derivative is negative, and derivative of cosine is negative sine, and will be positive sine. And then fourth derivative of sine is cosine. Okay, we can see we have, like, for this function, we have cycle of 4. Always the fourth, the multiplicity of 4 will be cosine. Yeah, because if we will think the fifth derivative, the sixth derivative, the seventh derivative, and the eighth derivative, it will be cosine. You can check this. And now, 8 now will be the 12th one. Shall I use the Roman? 12th derivative will be also cosine. All of the multiplicity of 4. And then 16th derivative, it will be also cosine. And then, let's keep working. How can I do this? Then we will have 16, what we need, 20th. I can maybe write here. 20th derivative will be also cosine. And then 24. I don't want to confuse you because maybe we don't. Yes, 24th derivative, it's also cosine. And now we need 27th because 25th, 26th, and 27, because the next 28 will be cosine of x. But we need 27th. Oh, where am I? 27th. Okay, 25th, derivative of cosine is negative sine of x. Derivative of negative sine of x is negative cosine of x, and that's the one actually. Derivative of negative cosine of x is sine of x. Well, you may probably do a little bit faster, but I was just gonna show you that the fourth one, the multiplicity of 4 will be the same. You can even check this, yes? You can check. That was 8. This will be 9th derivative. That will be the 10th derivative. 11th derivative. Okay, I'm using the Roman numbers. You can also learn Roman numbers. And then cosine, and then we can do this way. But every fourth multiplicity is cosine. And we need 27. 28 will be cosine of x. Sine of x is the answer. Beautiful. And the last question is this one. quite important. I mean, everything is important, but quite interesting. Evaluate the limits. Okay, we have 1, 2, and 3. That means we see the really interesting limits, but what is the point? The point is that my students will recognize that this limits represents the derivative of a certain function at a certain point. And I'm not really expecting you to solve this explicitly, yes, using some trigonometric identities, algebra. No, let's just use calculus. Because we can see this is the limit definition of a derivative. That means this is the derivative at the point pi over 3. And let's be more precise. Derivative with respect to x of the function, and we see this, sine of x, when x is pi over 3. Or a, I can say. Okay, that means we have to recognize that this represents derivative of the function sine of x at the pi over 3. Of course, the definition, let's say a, of the derivative is the limit as h goes to 0, f of a plus h minus f of a all over h. That's what we see, the evaluation for sine, cosine, and tangent. And maybe I can do a, just to be... Okay, that's mean derivative, let's see, derivative of sine of x is cosine of x, and we just have to substitute pi over 3. That means cosine at 60 degrees is 1/2. Okay, another one, derivative with respect to x of cosine of x at the point pi over 3. You can pause the video and then you can come back, and derivative of cosine is negative sine of x. At the point, I can put x. Pi over 3. Negative sine at 60. Negative square root of 3 over 2. And the last one is tangent. You can also do it. Derivative, this limit, yes, this limit represents derivative of the tangent of x at the point pi over 3. Derivative of tangent is secant square of x. And x will be x or a. I'm just, yes, interchanging pi over 3. And then secant at pi over 3, and we have to square it. Secant at pi over 3 is the reciprocal of cosine. 1/2, 2. 2 squared, it will be 4. Beautiful. Yeah? I mean, please look at these limits and try to, yes, recognize that they represent derivative of the certain function at the certain point. Okay, that means let's finish the session, let's practice, and what we have to know 6 differentiation formulas for 6 trigonometric ratio, respectively, of course. Okay, thank you. Enjoy the trigonometrics. Thank you.